post that later if anybody needs to see it. So just a reminder, related rates, first we read the problem, we determine what's given, we write it as reasonable variables, we write an equation that relates those variables, we take derivatives and we substitute back in our given information, and then we solve using units. Yesterday we talked about a cylinder and we had to use product rule for this problem. We also talked about a spherical balloon, and I reminded you that they will give you those equations. The spherical balloon was a little more challenging because it gave us two equations, and it didn't give us a dr dt, a rate that we needed. And so we had to take the derivative of both equations in order to solve one equation for the dr dt and then plug that into the other equation. So I want to go over the most missed Khan Academy problem from last night, just to make sure we're feeling a little more comfortable about these Pythag problems. They're very similar in the way they work for the most part. So this is, you might have had a similar problem or slightly different numbers, but I pulled this one from last night's homework. It said, a person stands 30 meters east of an intersection and watches a car driving away from the intersection to the north at 17 meters per second. So again, the reading here is really important, and it's very helpful if you can draw a quick sketch for something like this in general. So I have an intersection. I have an intersection here, right? There's a person standing. So there's a person standing over here. He's not moving. He's not walking around. He's not walking towards the intersection or away from it. He's just standing there. Okay, so he's at that point. And then we have a car driving away from the intersection. So that's important. And then it says north. Okay.
Wait,
if it said it was, yes?
Isn't the person standing east of the intersection? So it should be on the left side?
North, east,
does it not matter?
southwest, never eat soggy waffles?
Yeah, you're right. Yeah, you're right.
All good. I mean, call me out if I'm wrong. I very likely messed that stuff up, but I was pretty sure east was to the right. So yeah, so yes, but it doesn't really make a huge difference, honestly, in this one, if you have it to the left or not. But sometimes it will, so be careful. So it says that he's traveling away from the intersection, he's traveling north. So he could be traveling north and toward the intersection. So it's important that we know that he's actually traveling away. So he's going this direction up here. Okay, so that car is somewhere up here, but it's moving. At a certain instant, the car is 16 meters from the intersection. So in general, when we have these problems that are going to be triangles, I like to label stuff as X and Y. And if you get in the practice of doing that, it'll make it easier to come back and reference what thing you were actually finding. Okay, so we know that the given information, X is equal to 30. What's important about that 30? Someone unmute yourself.
It's a constant.
It's a constant. So we're going to write that it's a constant because we know with our constants, we're going to plug them in right off the bat as soon as we have our equation. Okay, so X equals 30 is a constant. Then it says he's watching a car driving away from the intersection to the north at 17 meters per second. Someone else, what would that information be?
dy over dt.
Perfect. So dy over dt, we talked about if things are increasing or decreasing yesterday. Would that dy over dt be positive or negative, Gus?
It'd be positive.
Why?
He's driving away from it, so he's heading like northbound. If he were to drive towards it, that'd be negative.
Correct, because the y value would be decreasing versus increasing. So you want to think about what's happening. Is it increasing or is it decreasing? Okay, and so that is equal to 17. And then it says at a certain instant, the car is 16 meters from the intersection. So someone else, what's that?
Y equals 16.
Y equals 16, perfect. Okay, now the question here gets a little tricky just to interpret. So I want to make sure we understand what we're finding. It says, what is the rate of change of the distance between the car and the person at that instant? So some people think you need like a distance formula or something like that. The distance, like how it's changing, is this length right here. That's the distance from the person to the car. And that we would normally just call R, but we are not looking for R, we're looking for what?
dr over dt.
Perfect. We're looking for dr over dt. So that's not information that we have, and we are looking for that dr over dt. We're looking for the rate of change. You could obviously label this with like an east and a north and a d or something. It doesn't matter. I just think it's helpful if you get in the practice of using Pythagorean triangles and x, y, and r, just so that everything is consistent. Okay, so someone else, what's my equation? I mean, I've already kind of given it away. What's my equation?
R squared equals x squared plus y squared.
Perfect, Pythag, right? So we're gonna use that equation. Now, I'm gonna plug in my constant right away. My constant is 30, so we're gonna have a 30 squared in there for an x. Now, the next thing I'm gonna do is I'm gonna take a derivative. So when I take a derivative of this, what do I get? Someone else. I like you guys just volunteering for now. I'll call in the spinner app in a second. But if I haven't heard from you today and you know the answer, go ahead and unmute yourself. What's the derivative?
The 2dr over dt is equal to 2.
Hold on 1 second, Brian. So the derivative of r squared is 2 what?
2r, sorry, 2r
there we go.
times dr over dt.
Good.
Equal to 2y times dy over dt.
Fantastic. Okay, I've got a 2 on both sides of these equations, so it's helpful sometimes to just cancel that 2 out. That will happen a lot of times when you're doing a Pythag equation just to make it easier. Now the issue here is I have y, I have dy dt, but I don't have r and I don't have dr dt. So what do I need to do, someone else?
You need to
x and y back into the original equation.
Yeah, I need to plug x and y back into the original equation so that I can find r. So Fallon, what should I type? What should I write down?
You should write down r equals the square root of x squared plus y squared.
Okay, and you want to just plug in those x's and y's. So what's my x?
Your x is 30 squared.
Good. Plus my
Plus
y is
16 squared.
16 squared. Now, for our purposes right now, I don't care if you grab a calculator and do this on a calculator. Just be aware, a lot of times you are going to be expected to do this stuff without a calculator, just for the purposes of times. We'll use that. So we get r is equal to 34. And now I can plug in all of that information, right? And you're welcome to isolate the thing you're looking for first, or you're welcome to plug in the information and then isolate, whatever is easiest for you. So we get 34, maybe I'll add that to my list of givens just so I can check it later. 34 times dr dt is equal to my y is 16 times 30. Nope, that was my, what's my dy dt? 17. Okay, so dr dt is equal to 16 times 17 over 34. So 16 times 17 divided by 34 gives us 8. What would the units of this be? Before I box it.
Meters per second.
Meters per second. Is that what's in the problem? Yes. So we have meters per second. You can show that as m per s, okay, because that's the correct abbreviation. Be careful though. If you're not sure, just write out the words. A lot of guys will make a mistake when I get to something that's like miles per hour and they'll write mph. That is not the correct abbreviation scientifically for miles per hour. So that would be counted as incorrect. So if you're not sure, you can always just write it out. Are there any questions on this one? I think you guys did decent on the Pythag stuff. I just wanted to go over this problem because it was one of the most missed from last night. On a first try. Most of you got it by 100% by another one. Okay, this is called, please write in your notebook, the shadow problem. So we talked about the ladder problem. That one is really consistent. This is another really common problem you're going to see, and it's called the shadow problem. So you don't need to write down all these things. I'm going to talk through how to approach this. There's kind of two versions of the shadow problem, and you're going to encounter both of them on your quest. So I want to talk through what to expect and how to deal with both of those. So it says a 6-foot-tall woman is walking at the rate of 4 feet per second away from a street lamp that is 24 feet tall. How fast is the length of her shadow changing? This is a super common question, and it's hard to think about, and it's hard to come up with the equation. Once you do, the math is super easy. So there's not a whole lot of complicated derivatives that you have to take here, but you have to know how to set this up, and it requires some knowledge of geometry. Okay, so first of all, let's read it again. A 6-foot-tall woman. She is not growing or shrinking magically during this scenario. She's walking at the rate of 4 feet per second away from a street lamp that is 24 feet tall. The street lamp is also not magically growing or shrinking. So the 6 and the 24 are both constant pieces of information. Okay, so I have a street lamp. Please draw this picture. I have a street lamp. And then I have some woman walking away from that street lamp. I'm just gonna make them both into lines. Let's try to make the bottom, oops, that was way too much eraser. Try to make the floor constant, so like, or perpendicular, I should say. So like, here's the ground. Okay, so I have a woman over here and I have a street lamp over on the left side. Okay, now there's a shadow that's formed. This street lamp is giving off light, right? There's a shadow that's formed on the right side of the woman in this scenario from that street lamp. And the way that shadow is going to be formed is that this is going to come down, oops, gosh dang it, and create a shadow. I'm going to get rid of everything else here. Okay, so I've got my woman. Maybe I'll give her a head and arms and a little skirt. Okay, and then I've got my street lamp over here. Now the woman is 6 feet tall. That's not changing. She's a tall lady. I'm a tall lady. That happens. Okay, we've got a street lamp that's 24 feet tall. That's also not changing. Those both are constants. So I'm going to put that into my picture right away because neither of those things are changing. Now, there's two different ways that you can label the additional information here. We have a distance that she is from the street lamp. Maybe I'll use a different color. We have a distance that she is from the street lamp. I'm going to call this distance x because it tells us that we have a rate at how fast she's walking away from the street lamp. So that information is going to be a dx over a dt is equal to 4. So we have a distance that she is away from the street lamp, and then we have how fast she's moving away from that street lamp, which is dx dt. Then we have her shadow over here. I'm going to call that S for shadow. And what we're trying to find is how fast is the length of her shadow changing. So what we're looking for is a ds over a dt. We don't know that information. That's what we're trying to find. Okay. So the idea here is we need an equation that relates this x and s. We have this other information about this 6 and this 24, and we're going to have to take some derivatives here. Does anyone, maybe even based on this picture, see anything that stands out to you, even if you just have a wild guess?
The triangles are going to have to be proportional to each other.
Excellent. The triangles are going to have to be proportional. So if you guys remember way back in geometry when we talked about similar triangles, what was true about similar triangles is this triangle down here, this like blue triangle, is going to be proportional to this bigger triangle, this yellow triangle. They're going to have some proportions in common. Okay. And the way that we would set up those proportions would be to say that, and you can pick which thing you put in the numerator and the denominator. Doesn't matter, just as long as they're consistent and the proportions are the same. 6 over s, that relationship, however tall the woman is, based on that part, since we have the exact same angle, since that angle is exactly the same, 6 over s is going to be equal to 24 over the entire base. And so the entire base is not x, the entire base is x plus s. Okay, so those are similar triangles. This is how you're going to set this up every time with a minor exception, and we'll talk about the different type of shadow problem that you're going to see, but it's still going to be similar triangles. Your variables are just going to be a little different. Okay, now from here, this looks like kind of a messy derivative to take, and I've already plugged in my constants. I've already plugged in my 6 and my 24 into the equation. Okay, I don't recommend you take the derivative like this first. I recommend you multiply, you cross multiply, and then simplify this equation prior to taking a derivative. So when we cross multiply, we're going to get 6 times x plus s. So that's 6x plus 6s is equal to 24s. Already that's a much easier thing to take a derivative of, but we can go even further by combining some like terms. If I subtract the 6s over, I'm going to get 6x is equal to 24 minus 6, so 18s. That's our equation, and the equation is really basic here. So the hardest thing is to remember to set up the similar triangles and to kind of label your picture with some reasonable variables. From there, the derivative is really easy. Aiden, Lynn, what would the derivative of 6x equals 18s be equal to?
It would be equal to 6 times dx over dt equals 18 times ds over dt.
Absolutely correct. So some guys get worried, like, how do I solve for x and s? Like, how do I figure out where she is? You don't even need that information, right? Because from Aiden's derivative, we have dx dt, we have 6 and 18. All we're looking for is ds over dt. That's it. Okay, so now I can solve for that. We're going to have, if you want to divide that 18 over and simplify this, you can. So 6 over 18 is the same as 1/3. So you could make this 1/3 times our dx dt, which was 4, is equal to ds over dt. Just in case you zoned out for a second and wondering where that 1/3 came from, I just divided the 18 over to the other side, simplified as 6 over 18 into 1/3. And so that's our answer. ds over dt is equal to 4/3. What would the units of that be equal to, Dennis?
Would it be, oh wait, oh sorry, feet per second?
Perfect. So Dennis was reading back in the problem. That's exactly what you should do. Go back, skim, look for where we had those units, make sure our units make sense, right? Just feet wouldn't make units. It has to be a feet per second. Dennis, does it make sense that we got a positive value out of this?
Not, thinking about it, I don't think so, because like she's getting farther away and like, I don't know. It's
hard to think about this one, right? It feels like it should be getting smaller because she's getting farther away. But what actually happens as she moves farther away, like think about if she stands just right here, right? If she just moves a little bit to the right, sorry, she grew a little taller there. Let's try to make her exactly the same height. Okay, now the shadow is going to be longer because now that angle is going a farther distance. So it's hard to think about, but yes, it should be growing as she walks away, even though she's getting further away. Okay, and you can think about it like if she were to stand right underneath the street lamp, her shadow is almost non-existent. It's a little bit bigger as she starts to walk away, and it gets longer as she walks even further. Okay, I want to talk about a slightly different question you're going to see, and you're going to see one on Quest that's like this, and we're just going to talk about if they give you a different piece of information. Sometimes the question won't ask how fast is the length of her shadow changing. Sometimes it will say, how fast is the tip of her shadow moving away from the base of the pole? Okay, so on this case, we were looking for how fast this distance was changing here, right? Sometimes instead, it's going to ask how fast is the tip of her shadow, this value, whatever the tip of her shadow is, how fast is that moving away from the pole? Okay, and so that means we're going to need a different variable. If that would be the question, you're still going to have a similar triangle here. You're still going to have those two triangles that we can see, okay? But instead of labeling, you'll probably be given how fast she's moving away, and I would call that x. But it's not helpful to call this variable s because I need to know the total length that it's changing. So what I would do is I would make that variable x, and I would make the total distance the variable L is for whatever reason something I usually choose, but you could call that one S if you want. I'm just going to call it L so it's different. Okay. If this was the same scenario, but I wanted to know how fast the tip of her shadow is moving away from the light pole, this is still 6. This is still 24. Now what I'm doing is I'm setting up 6 over what? What would be the denominator? Instead of 6 over s, now I don't have a variable for this part. What would go in the denominator there? Anybody?
L minus
x.
L minus x. You guys got it. Okay, so L minus x, and then it would be equal to 24 over what?
L.
L, perfect. So it's a little bit of a different equation, exact same setup, exact same next process, you multiply, right? And then you simplify your like terms and then you take a derivative. Are there any questions on the shadow problem? Shadow problem is not that hard if you understand the setup. Like the derivatives are quick, no product rule, no chain rule, no quotient rule, or I guess chain rule because it's implicit differentiation. But basic stuff with usually pretty easy math, you just have to know the setup. You have to know which problem you're kind of solving for. No questions?
Ms. Tosher.
Yes, sir.
So why did you change from S to L?
So in the first question, George, it wanted to know how fast was her shadow, the length of her shadow changing. So the length of her shadow is only the distance from that person to the end of this triangle. That's the length of her shadow. What you're going to also encounter sometimes for a shadow question with related rates is it won't ask how fast is the length of her shadow changing. It will ask how fast is the tip of her shadow moving away from the base of the lamppost. So it wants to know that tip of the shadow, not how much faster that piece is growing from the person, but how fast that dot, the tip of her shadow, is moving away from the light pole. So the reason we chose an L is because I am actually looking for a DLDT in this kind of a scenario. I need to know that total distances change. And if I just have X and S, I don't have a variable that's going to help me determine that information. Great question. Other questions? Okay, let's go on to another problem. This is number, I don't know what really, I've added some Khan Academy questions in here, but I think this is number 6. Okay, this one is tricky. It appears really, really tricky, and we're going to talk through how to approach this one. So it says a television camera at ground level, a television camera at ground level is filming the liftoff of a rocket that is rising vertically. The camera is 2,000 feet from the launch pad. The rocket's velocity is 1,000 feet per second. Find the rate of change in the angle of elevation between the camera and the rocket when the rocket is 5,000 feet off the ground. So let's draw a picture. Often that's helpful. It's not always necessary to draw a picture. We did several problems where we didn't draw pictures. This one sounds like it's going to be helpful to draw a picture. So I have a rocket. I wish I could draw a straight line. That would be so nice. I have a rocket. It's taken off. Here's my rocket. Woo! Okay. I'm such an artist, guys. And then I have over here somewhere, I have a little camera. The camera's watching the liftoff and it's in the ground. Okay. And it's like in the ground. It's ground level. I think it says that. Yeah, at ground level. So it doesn't have any height associated with it. It's in the ground and it's watching that liftoff happen. Okay. Take a second and write down your given information. I'm going to give you guys a minute to write down your given information. Again, we're dealing with a triangle, so maybe choose variables that we've been using. Make sure you label anything that's constant. All right, JJ, I'm coming to you. What do you got?
So I wrote C equals 2,000.
What is C?
I just put the distance from the camera to the base of the rocket.
Okay, can I make a suggestion, JJ?
Yes.
Can we call this X and this Y?
Yes, let's do that. So I put X equals 2,000. Then I put DH all over, or excuse me, DY all over DT equals 1,000. And then I just put Y equals 5,000.
Okay, I think that looks good so far. Okay, there's some important information I want you to include within those 3 things. Okay, anything you would add to that, any of that information?
Yes, the hypotenuse or maybe the R.
So we could find the R. That's something that we could find, right? Because we have our 2,000 and our 5,000 for our X and our Y. So that might be useful to find. So yes, I am going to want that also. What is important about that camera and its placement, JJ?
It's unchanging, doesn't change.
Correct, it's constant, right? So that is not some camera guy walking around. It's a camera in the ground and it's just tracking, right? So that's a constant, so we always want to label that. But yes, we also want to find our R. So that's exactly right. JJ recognized, well, we have a triangle here. We have X and Y, so we can probably find R, and that might be useful. Take a second, find your R. It's not, don't write it as a decimal. It ends up being square root of something. So let's go to Ryan. How would you find R?
Wouldn't you just use the
Oh my God, so much feedback, Ryan. Hold on, I'm gonna come back to you in a second. Justice, how would you find R?
You could set up R squared equals 2,000 squared plus 5,000 squared, or just R equals the square root of 2,000 squared plus 5,000 squared.
Perfect. Okay, so we get R is equal to, I think we get like 29 million out of this.
Yeah.
2 squared is 4, 5 squared is 25, 1,000 times 1,000 is a million, right? So we get 29 with like 6 zeros after it, which, to simplify by hand, which I would expect you to do on this one, okay, this would definitely be a no calculator problem. Even though it looks really hard, these numbers are not hard. You heard how I did that math. 2 squared, 5 squared, those are easy things to think about, okay? We end up getting 1,000 out of this square root, right? Times square root of 29 inside of that square root. Okay, so that's our R equals. So I'm gonna add that over here to JJ's list of given information. 1,000 times the square root of 29. Okay, one of the hardest parts about this question is actually figuring out what it wants us to find. Okay, a lot of times it'll say like, how fast is the rocket moving away from the camera? That would be like a DRDT. That's not what this one says at all. This one says, find the rate of change. So rate of change, that's a D something in the angle of elevation between the camera and the rocket. Does anyone have a guess at like what they're asking us to find here? If you had to make a guess, a rate of change, go ahead.
d theta over dt.
You are so smart. D theta over dt is actually the thing we're looking for. Okay, d theta over dt is what we're looking for. So theta, again, is this angle right here. That's our theta. And that's exactly the right variable you should choose, is a theta to represent an angle. D theta dt is how fast that angle is moving, right? So how fast that angle is changing. That's what we're looking at because the camera is tracking the rocket. So this is a little bit of a new one. This isn't gonna be a Pythag. We used Pythag to find a piece of given information, but our equation needs to have a theta in it because in order for me to take a derivative and get a d theta dt, I had to start with something that has a theta in it. Okay, so there's a couple different equations you could choose. I'd like everyone to try to write down an equation. Don't do anything after that. Just try to write down an equation. There are multiple equations that you could write down, by the way. Multiple things are going to work here. There's not one way to do this problem. I'm gonna pick a way that I like best, but there's not one way to do it. Think about what would make your derivative easiest, would be my hint in writing this equation. Okay, so I don't want to waste too much time. We've got to use trig, right? I've got theta in here, so I've got to use trig and I've got to use some relationships. Basic trig, sine, cosine, or tangent. Those are our basic ones that we're probably going to come to, right? If I wrote a cosine equation, cosine of theta is equal to x over r. If I wrote, let me give myself a little more room. Excuse me. If I wrote cosine theta, we know cosine theta is equal to x over r. If I wrote sine of theta is equal to y over r. And if I wrote tangent of theta, tangent of theta is equal to y over x. That's basics. Back in, hopefully you're not still doing SOHCAHTOA. This is easier to think about. That's again why we use x, y, and r, so that we don't have too much extra thought process here. But that is SOHCAHTOA if you labeled it according to x, y, and r for this triangle. That cosine theta equals x over r, sine of theta equals y over r, tangent of theta equals y over x. Now, one of these is going to be most helpful to use, and there's a reason for it. So think about if I were to take the derivative of cosine of theta equals x over r. I know I'm going to have to use quotient rule probably here. And I know I'm going to end up with a dx dt and a dr dt. Neither of those pieces of information do I have. I don't know what dr dt is, and I don't know what dx dt is, and I don't know what d theta dt is, and I don't have a way to find those things. That is not going to be our best equation to use. Okay, sine of theta. So again, sine of theta, also going to need quotient rule here, y over r. Again, this time I do have dy over dt, but I don't have dr over dt, right? So I'm not given a dr over dt. So this one's not going to be as helpful either. Now let's look at this last one, tangent of theta equals y over x. So again, it looks like quotient rule. And again, it seems like we don't have one of the pieces of information. We don't have dx dt, but secretly we do. We do know what dx dt is because x was a constant. Right? So if x is a constant, it's a constant 2000, or dx dt is 0. And even better, with a constant, I can plug it in right away. So because it's constant, I can actually avoid my quotient rule. So we are going to choose this last option. We are going to choose to take tangent of theta equals y over x as our equation that relates our information. And we're going to plug in our given information right away. That is a constant. So any constants get plugged in right away. So that gives me tangent of theta. Oh my gosh, what's up with my screen? Tangent of theta is equal to y. Y is not constant, right? The rocket's moving. So y has to still be in there, over our x, which is 2000. There's a bunch of different ways you can write this. You could write 1 over 2000 times y. I think most people will find it easier to just multiply that 2000 up to the other side so that they change their starting equation to 2000 tangent of theta is equal to y. Most people will use this as a starting equation just because that's a little easier to think about the derivative, right? So I want you to take a second and write that derivative. Something that's easy to miss here, so be careful. The 2000 tan of theta equals y. You might have to look up your derivative of tan. Hopefully you guys are starting to remember some of those trig things. Again, flashcards are really helpful for that. Just grab some note cards, put the trig derivatives on the other side. Let's go to Conrad. Conrad, what'd you get for your derivative here?
I got 2000 times secant squared theta equals dy over dt.
So I am assuming this is what most of you have. This is really, really, really close. Here's the problem, Conrad. We're looking for a d theta dt, and we didn't get one out of your equation because you forgot the chain rule in the tangent of theta. Right, for tangent of theta, our inside function is theta. So when I take a derivative of that, I need to multiply by the derivative of theta with respect to time. So I am guessing what Conrad had is what most of you had. There's an important thing missing, which is the thing we're trying to find. You should have a d theta dt being multiplied by that secant squared theta. And then everything else looks good, equals dy over dt. Like I said, this is a no calculator problem. Do not touch your calculator on this. You would not be given a calculator. This would be in the no calculator section. Even though it looks really hard, Dennis is like putting his sheath on his calculator and putting it away. I like it, okay? This is not a calculator active problem. So let's isolate these variables really quick. So I'm gonna isolate my d theta dt. To do that, I'm gonna divide over the 2000 and the secant squared. So I'm gonna open up a new window just real quick. If you're like, where did everything go? I'm just moving it around, okay? So we have d theta over dt is equal to dy over dt divided by 2000 times secant squared theta. Okay, so all I did was I took that equation over here and I divided over the 2000 secant squared to the other side. So we get dy dt equals, d theta dt equals dy dt over 2000 secant squared. This is where trig identities comes back in from last year. If I'm dividing by a secant squared, that is the same as doing what, Gus?
Would it be, would it be multiplying it by a cosine squared theta?
Exactly right. It would be the same as multiplying by a cosine squared. So really what I have here is dy dt. Oh, I don't know why I'm writing that so big. Dy dt over 2000. And then you can move the cosine squared up to the numerator, or you can just write it as multiplication, whatever feels easiest to you. Okay. Now the issue here is we don't have theta. So a lot of guys are like, how am I supposed to find cosine squared if I don't have theta? Like, it's not a special triangle, right? It's not something that I can easily find the theta for. But again, I don't actually need theta to find cosine theta. If you guys go back, cosine theta is just a relationship between two sides of our triangle. Cosine theta is x over r, and I have both of those pieces of information. So I don't need theta to find cosine of theta. All I need is an x and an r. So if I go back, my x was equal to 2000. And my r was equal to 1000 times the square root of 29. That simplifies quite a bit. Cosine of theta is equal to 2 over square root of 29. Again, you don't need to rationalize this. Don't waste your time doing that. Now, as part of my equation, I don't need cosine theta. I need cosine squared theta. But that just means I'm squaring this value. So like cosine of theta squared just means I'm squaring both sides of that. So I would get 4 over 29, and that's going to go in for cosine squared theta. Okay, go ahead and plug in the rest of your information, see what you get. Let's go to Nathan Wise. So d theta over dt, Nathan, what did you plug in for your dy dt?
It would be 1,000.
Great.
1,000 over 2,000 times 4 over 29.
Perfect. Okay, so you can simplify some pieces of that.
So the first, you can simplify it to 1/2.
Perfect.
4 over 29. You can also just simplify the 2 and the 4. So it'd be 2 over 29.
Perfect. And notice we didn't need a calculator. We really actually didn't need one. Like, this was not a hard math problem algebraically. Okay, you had to use some knowledge, you had to think through it, but this would not be a calculator active problem. These are pretty easy numbers they gave you. Okay, harder question. Does anyone know what the units of this is? So we found d theta dt.
Oh, degrees per second.
So that is what a lot of guys will say, and that is close but incorrect. Any backup guesses, plan B guesses?
Radians per second?
Radians per second is correct. Radians are technically unitless. Okay, so if you looked and actually like figured out what units I got, like for cosine theta, we had an x over r. I think this was in feet per second. Yeah, so we had like a feet over a feet here. So that cancels out and it's unitless. Radians are technically unitless. And also, just a hint, We are never going to use degrees in AP Calculus. We are exclusively going to use radians. Okay, so if you're wondering if it's degrees or radians, it's always going to be radians. We get 2/29 radians per second. Fantastic job. Are there any questions on any part of this problem? This is a tricky problem. I go through exactly this, and then I usually put a question like this on our quiz or a test, and it's the most missed question, just because guys are like, wait, how do I find theta? Or is it a special triangle? And neither of those things are important. All we were, like, the key here was the setup, picking the equation that was most beneficial to us, which was the tangent theta, excuse me, and plugging in that constant information, and then noticing that for cosine theta, we don't need our theta in order to find that information. Okay, any questions there? Any questions on any of this? Okay, so tomorrow is a quest day. It's a quest day, it's a quest day, it's a quest day. I expect you to work on quest for the duration of the period, unless you're done. And some of you are probably gonna finish tonight because you already got a head start, so kudos to you. If you are gonna be gone tomorrow, I expect you to spend some 50 minutes today at some point working on your quest. I highly encourage you, if you're on campus tomorrow and you're working on this, to go to a place where there are other students in my class. So quiet room, great hall, SAC, those are good places. I think that a lot of you end up being on campus. That way, when you get stuck and you have a question, you can lean on each other. Do not save this for Sunday night. There are not that many questions. They will take you way longer than you think they will. Okay, so make sure that you are really working on it. Get a head start today if you can. That'll really prep you for tomorrow. And then tomorrow you're spending the duration of the period working on quest unless you're done. Okay, are there any questions on any of this? How are you feeling? Great, terrible, somewhere in the middle? Thumbs up, yes, that's what I like. Some of you don't have thumbs. Some of you are in the middle, that's good. Okay, all right. If there's no more questions, I'm gonna let you go a little bit early. You got an extra 5 minutes, sweet, that's excellent. So go stretch, take a bathroom break, get a snack or something. If you have any questions, I'll stay on afterwards. Otherwise, have a wonderful day. Have a wonderful weekend. Be safe, make good choices. I will see you guys Monday.
Thank you.
Thank you.